Okay, so they added the word AI to the title of the talk, so I didn't have it. Okay. I hate the usage, but I think Karthik wanted to ensure that it's not some other kind of foundation model, because the word is used, abused, and so hopefully I don't fall in the abused category this talk. Okay, so I'm going to talk largely about things we're going to try and do. So it's mostly about new ideas. And the core question that we're after is whether text-based representation can beat graph-based representation. Right? That's sort of the underlying question that we're trying to go after. So in 2020, one of my close collaborators built, at that time, probably one of the first chemical foundation models with Camberta, and he trained it on 66 million molecules from PubChem. He was far from graph-based models, and I was like, come on, this is like a waste of time. Why are you doing this? Blah, blah, blah. Fast forward to 2023. At the beginning of this year, IBM largely just scaled it to 1 billion molecules, right? And they built Molformer. And suddenly now it's beating graph-based models, at least in certain tasks. And so I think that's I had to sort of swallow my pride and say, Bharat, you got it right. Except the one thing I told him is, even if you think that this is not going to work, patent the idea, right? He didn't do it. And so now IBM's off to the races commercializing it. The core question, right, is why is it that we think that graph-based models, right, are good? And I think I'm going to try and argue why I think text-based representation might have a shot at just beating all kinds of models that we might conceive. Okay, so the canonical workflow in material science is the following. So you have some representation. If you have a molecule, that usually is called as SMILES. If you have a crystal, that usually is called a CIF, crystallographic information format. Right? These are all text-based representations of the molecule or a crystal. And then what you do is from the SMILES or from the CIF, you can generate a structure, right? That structure has connectivity information and so on. And then with that structure, you can then construct a graph. And from that graph, you're able to predict performance, right? And so in text-based representation, all you have is either the file, the CIF file of text, or the SMILES representation. And we're sort of trying to go from just that to the answer. Okay, so I'm just going to sort of give you at a high level how to think about this, right? So how do you think about a molecule as a string, right? So basically what you have here is you have some complicated molecule here, and then you basically do first sort of a depth-first traversal. So you basically have that green line that is collecting the chain of atoms. And then once you have these branching, right, those atoms are then labeled, and then the branching is shown. And then basically from that, you can uniquely reconstruct the molecule. Okay, this is a very old representation. This was something that was invented in the 80s. It turns out that SMILES is not sort of a unique representation in that if I generated arbitrary SMILES, right, that would not give me valid molecules. So there's a minor variation of it called selfies, right? So they love coming up with cool acronyms in this field. Selfies is 100%. So every valid selfie string is a valid molecule. Okay, so that's molecules as a string, right? And so what's sort of the state of the art, right? So we've done a lot of work on graph-based models, and the idea of a graph-based model is the following, right? You have atoms. The atom itself is a node, and then the bond is basically an edge in a graph. And basically you have node feature vectors and bond feature vectors, and then you do regular operation, right? So it's basically no different than how you do numerical methods on a grid, right? Crystal graph convolution effectively is like doing finite difference, right, on a grid of atoms, right, instead of sort of grid of simulation variables that you have. Okay, so the state of the art today for sort of energy predictions is a class of methods called crystal graph attention network. Attention is just a type of architecture of how the information passes. And NEQUIP is basically an equivariant neural network that basically embeds the symmetry of the crystal, especially rotational symmetry. Okay, so the question that we set out to answer with this Catalyst project, and I guess it's already been catalyzing a lot of thinking, is the following, right? So if you look at sort of this is the sort of classic computational cost versus error plot that you see in many fields, right? So in material science, right, there's sort of two frontiers. The right side is sort of what we notionally consider as ground truth, which is density functional theory or quantum chemistry, and then on the left you have empirical potentials, right? So these are sort of handcrafted functions that you use to sort of predict how things behave. And then there's a large body of work that's happening on what's called MLIP, which is machine learning interatomic potentials, which are basically different functional representations for those empirical potential. The question that we are setting out to answer is, can we build foundation models, right? I'm going to define what foundation model is in a bit. Can we build foundation models that are much cheaper than ground truth with quantum chemistry or density functional theory, but then basically now have the same kind of accuracy, okay? And the core thesis that we are after is scaling up, okay? The journey I told you was the first scaling was from 66 million to 1 billion, right? That had sort of an order of magnitude improvement. The question is, will that continue? And so that's sort of the question that we're after, okay? It turns out that, it's very easy to get molecules, right? All you need to be able to pre-train here is you just need a valid molecule, right? And so there are actually catalog of molecules. The known chemical space, right, is of the order of 50 billion. This is synthetically accessible, right? This is molecules that someone can make, okay? So the core idea here is basically now we do pre-training on this, corpus of 50 billion molecules, and we're going to do some interesting things to the architecture there. That then gets us to pre-train foundation model, right? That gives me now a representation for every cell, every SMILES, right, or every molecule. From that, I can then fine-tune for different kinds of property prediction. Right? I'm going to show you what are the kinds of things that we could do. And so it's fairly easy. The right two are very easy, right? We can use that to generate new molecules, properties, and so on, okay? One of the things that we put in this Catalyst proposal, which the reviewers asked a lot of intriguing questions, right, is we said that we want to test emergence and emergent behavior. Right? And what is emergence? How do you define emergence, right? So I'm going to try and sort of address a few of these questions. Okay, so what is the sort of core idea here of what we're going to try and do? So I'm going to just jump into sort of what the high-level core idea is, right? So you have some SMILES representation, right? And that SMILES representation, right, you can think of as broken down into sort of, smaller strings, right? That basically forms the vocabulary, right? So that forms sort of the way in which you represent chemical space, right? And then you pass that through some encoding scheme, right? There's a different kinds of positional encoding. We'll come back to that in a little bit. And then the task you're trying to do, right, is you mask that, right? So just like language models where you're trying to predict the next word, here you're masking a portion of that string. And then with all the information that you have, can you predict that label back, right? So it's effectively the same as the sort of sentence completion problem, except that in sentence completion, usually what you do is you do causal, which is that you don't know what the future is, right? But with molecules, right, you have sort of the rest of the molecule. And so you basically are trying to do acausal models, okay? Now what you do is with this, you get...
Training it. In pre-training, it's the same, right? Because there also how is it in the pre-training?
Well, in pre-training, even in the pre-training case, you might or you might not want to do that, right? In language models, but here we would not do it.
Okay, so it's an option there.
It's an option there. I mean, here we would not. We would keep it, right? We would not do causal. Okay, so this sort of opens up sort of a slew of things that we can do. So I'm just going to sort of talk at a high level. There's sort of three main parts to this, right? The first one is the representation, right? How do you give the identity of the molecule, right? So I talked about two things, SMILES selfies, and there's also an XYZ file, right? Which is basically the XYZ coordinate. So now that's essentially actually going closer to a graph. And so the question is, can we now give the graph itself in a text-based format? Tokenization, right? This is sort of the fancy way of saying, how do you break down and create your vocabulary, right? So there's few clever ways in which we can do that. And then position embedding, right? Here, right? Position embedding is where is the position, right, of whatever chemical species that you are representing. It turns out that everything in your gut should tell you that position embedding should matter. Absolute position embedding means that basically you just put the absolute position. Rotary embedding means that there should be, the problem is rotationally symmetric, right? It shouldn't matter if I read from left to right or from right to left, right? A molecule is a molecule, right? So rotary embedding should matter. The current results show that it's not the case. And so we're going to sort of look at this sort of size of chemical space. Okay, so once we have this, right, we have now a pre-trained representation, right? From that pre-trained representation, we can now do all kinds of things, right? Which is property prediction, generation, and other kinds of tasks. And so the hope here now is there's a very large corpus of very high quality quantum mechanical data of the molecular levels, the highest occupied and the lowest unoccupied molecular levels, which turns out to be a very important property when you try to design molecules for energy storage. And so there's an 86 million molecule calculation data set that has come, which we're going to put to the problem here after pre-training on this 50 billion corpus, fine-tune on that, right? And so that's sort of the gist of what we're going to try and achieve here. And I'm going to sort of talk about the opportunity space, right? So if you sort of look at the space of molecules currently explored, right, in the energy storage space, right, that's of order 1,000, right? This is all of the molecules that have ever been put inside at testing of a battery, right? The drug discovery space is a little ahead, right? 2 more orders of magnitude. And then, of course, ChemBurda is, as I said, so it was trained on 70 million, right? And then Molformer now 1 billion. And the hope here is now with this very large corpus of data with Enamine Rio, we're going to sort of open up chemical space and do things that was previously not possible, right? Question is, does this really make any sense? And so here's a visualization that shows you, right? Here's now a visualization of the chemical space that's been explored. And so this is the size of the pre-training data set, right? And you see that all the battery molecules that have been used, right, are all in like very few quadrants, right? So there's a large portion of chemical space that hasn't been explored. Okay, so now one of the things that you need for doing.
I know it's more like a it's more like a schematic, but what exactly does that represent?
Yeah, so you can visualize this in a variety of ways, right? So this is with sort of one kind of featurizing scheme, right? Showing how different they are in chemical space. Okay, and of course that's sensitive to the featurizer. That's sensitive to sort of how you do it.
Wondering what this feature is. What is the featurization for?
I think this is basically one of the sort of standard featurizing that we use in either one of these fingerprinting techniques, right? Nothing sophisticated here, just normal chemical fingerprinting. Okay. All right. So in order to be able to train this large a model, right, you need sort of very large compute. And so we've had the sort of good fortune of being having had access to Cerebras, which is wafer scale computing, right? So these are basically now whole wafers, right? Instead of these sort of dies that are separated, now you have a massive AI optimized 850,000 core system. We had built one of the earliest machine learning interatomic potentials, the MLIP that I had in the previous slide. We had trained one of the first ones with CS1, Cerebras 1, that was originally in the Pittsburgh supercomputing cluster. Now there's CS2, which is basically, I think there's one in PSC again, and then a few in Argonne. And we have access. We've had early access, and we continue to have access here. And with this, what we'd like to do, right, is to try and explore the sort of compute optimal scaling This is a very busy plot, but all I want you to sort of take away here is the y-axis is model size, x-axis is the training flops, right? And these are ISO loss contours, right? And so what you want to do, right, is you want basically the lowest possible model size and the lowest possible training flop for a particular error, right? Which means that you basically have that straight line there. That's basically the efficient computing frontier, right? That minimizes loss, while at the same time make sure that you're not wasting compute and model size. And so this is for large language models. We want to try and explore this for material science. So that's sort of what we're out to try and do. Okay, so the last question, this is actually inspired by some very thoughtful reviewer comments, right? So hopefully this sort of starts down this part of emergence. And there's two ways in which we can think about emergence, and people fight whether there is emergence or not. Right? Every graduate student in the room has felt emergence, right? They start in their first year, they know nothing, second year, third year, and then suddenly they become very, very good, right? And so the hope is that these models also, right, exhibit this behavior, right? I mean, someone has to tell you the truth, right? Okay, so that's emergent ability, right? The interesting thing is emergent techniques, right? And the emergent techniques here are things like, chain of thought, right? Being able to have a scratch pad, right? Being able to do this sort of 8-digit addition. So we were thinking about what are the sort of tasks, what are the sort of emergent tasks in material science? And essentially what this is, right, is what would you be doing in high school, right? And so I was like thinking about what was I doing in high school, right? And so I was going to I went to the International Chemistry Olympiad. And so you had all these like very interesting questions that are effectively sort of computational puzzles, right, in chemistry, right? They would give you things like NMR spectra, like broken down moieties or mass spectra. And then you ask the question of, given that information, can you now reconstruct the molecule, right? So that's basically sort of a mathematical task. And so the question that I think on the emergence side on the ability side that we're keen on trying to explore is, can we now use these models to construct reaction graphs and so on? Okay, I have hopefully 5 more minutes. Okay, so I'm going to show you one last thing, right? Super new, but one that I think would be very interesting, and I'd love feedback from this community. So this is a robot that we had built, which basically can move in chemical space. So the robot basically has a bunch of vials. The vials have different ratios of chemicals. You can mix them in various ratios. Depending on how much you mix, you can move in chemical space, right? And it goes and makes a bunch of measurements. It's all connected to an optimizer, and it's all fully automated, no human involved. So we can do lots of cool things with it, right? So we can do sort of mathematical tests on this. So the middle is what we use routinely with this test stand, right? The test stand is called Clio. The optimizer here is Dragonfly, which is a Bayesian optimizer. And it has a bunch of different sampling strategies. Here it's showing that it's able to find sort of a maximum in conductivity. And Bayesian optimization here, has a few different ways of exploration and exploitation. I'm not going to sort of talk into the details of it. The package is called Dragonfly. The right side is sort of fully gradient-based optimization in this chemical space. And here what we have taken is we've taken the graph representation of these molecules and then used a lot of data, right, to be able to build gradients in chemical space, right? And we validated that these gradients are good at finding the optima, right? So obviously finds the optima much faster than Bayesian optimization. Okay, all right, so here's a crazy idea. Okay, so I'm going to start with crazy because then you don't have to say it's crazy, right? The question is, can we use large language model as an optimizer? Okay, and the instinctive reaction should be that, oh my God, that's so stupid. Right? Because why would you throw away all of this information that you knew about the problem, right? And why would you use LLM as an optimizer? And I'm going to sort of try and walk you through the reasoning for why I think this is a pretty interesting reaction. Okay, so the framework is the following, right? So I have what I'm trying to do is I have some set of variables, right? Compositional variables, And from that, I'm trying to predict some property or measure some property. And then that then, of course, connects to some functionality. And so the question is, can I now use this as an optimizer? Okay. So one of my students came up with this cool graphic yesterday. So I said, it's so crazy, it just might work. Okay, so what is the core idea here, right? It's often when you're doing optimization tasks, you usually construct some continuous variable, right? Or discrete variable. But that variable is often not all that you know about that system. You actually know a lot more about that system than usually you can give in the mathematical function that you're using to optimize, right? So it's clear that LLMs can exploit priors from large-scale pre-training, right? So you can give it a bunch of questions, right? And somehow it's able to sort of do classification, regression, inverse design, and all of these priors. So we're now sort of flipping this and saying, can we now do this where this is a true optimizer, right? Like this is not cheating, right? So what it's doing is you basically go to one of these, and actually this is UMGPT-4. It turned out that the GPT 3.5 was worse than the UMGPT. So kudos to the team for building that capability. And so what we do here is basically, I'm sort of embedding all of the knowledge I have about that system in that first step, right? I say, here's all that I know about the system, right? Now, I now started with this composition. Give me a recommendation for the next composition, okay? And because our test stand is basically fully automated, right? You can basically chain the API call, get the answer. The answer is actually a very reliable JSON. That JSON gets read and then fed into our system. So you actually truly are using this LLM as an optimizer. Now, of course, if you naively try it, right, it'll do all kinds of bad things, right? It doesn't have memory, right? So it's not a self-avoiding walk, right? So you need to sort of give it the chain. And so with sort of, I guess now we're just going to be producing generation of prompt engineers. So this is some very good prompt engineering by Shang here, right? And so this is now that same chemical space that I showed you with the gradient-based optimization, right? But now we're doing that with the LLM, and you actually see the right trajectory is really interesting, right? It actually very quickly finds that you want to go low in EC composition. Okay, and the way that comes in is we tell that the ethylene carbonate has a very low melting point, and so that it knows that it's a solid at room temperature. And so what this is, I think, showing is that this is sort of a very new frontier. Okay, and I think thanks to, I guess, the Catalyst program, I think it's already catalyzing. There's a bunch of things that happen. So we got Microsoft's Accelerate Foundation Models Award. So we now have access to the latest in foundation models, GPT-4 and so on. And I think, about 3 or 4 years ago, I launched sort of the SciML series, which was sort of talking about the fusion of machine learning and scientific computing. I think there's a huge opportunity now in building scientific foundation models. I think this is going to become the pillar on which every simulation frontier is going to emerge in the future. And so I want to give a shout out to my close collaborator, Bharat at Deep Forest Sciences, who's deployed the first set of chemical foundation models in Chiron. And we have beta access to Chiron. So anyone that wants to look at foundation models for material science. And we're trying to see if we can use these same ideas for other kinds of simulation. And so with that, thank you for your attention. And thank 3 people that did all the work, Anushka, Alex, and Shang. Right, they're the ones that made the slides till the 11th hour, especially Shang with prompting, I guess, the GPT-4 yesterday at midnight. And so thanks for your attention. Happy to take questions.
It was fascinating to go always. So are you actually write a cost function, or I mean, you do talk about the elements of on that.
Yeah. So we do say that your task is to optimize the electrolyte mixture composition to achieve highest conductivity. So we could give it some we could give it some weight cost function which I think is an even more interesting one where the mapping is not clear. So there's a weak mapping between ionic conductivity and fast charging. But we could say, just optimize fast charging for me, right? So here it's a more specific task because conductivity is a direct measurement that we can make. And so every time what we do, we get the answer, and then we get the output of that Clio robot to the LLM. So it's a true optimization in that sense, right? So you give it the trajectory of, you give it the history of whatever it has seen, and then the next answer, the next measurement.
Not the obvious line, this is the four slide when you have the graph about accuracy.
Mm-hmm.
So yes, so okay, maybe I've not understood this correctly, but so are these the techniques which you show on the graph, the ones which you're using?
Yeah.
In the the training model is created using these methods, right? And then you're going to train on top of this to predict what you want to predict. So is that right? Is that assumption correct?
Yeah. So the pre-training is not done on any of that, but the fine-tuning is done on data using the DFT data on the right.
Okay, so
we're not using those two as data points for fine-tuning.
Okay, excellent. So so do you think that the accuracy, which I mean DFT is pretty accurate, but do you think the accuracy of DFT is sufficient for getting sufficient accuracy for final things you're trying to use? Because for example, like you mentioned quantum accuracy, which is why DFT is not very quantum.
Yeah. So actually it turns out that our fine-tuning is going to be on quantum chemistry calculations, not at DFT level. But I think the larger question you're asking is whatever you're going to train, whatever accuracy you get, is it sufficient for the task you have at the end, right? So what is the task you have at the end, right? And I think this is the important insight. The task you have at the end is one of what's your next move, right? You have some set of information about what you've tested, what molecules you've tested, what compositions you've tested. And your next move is to decide what new composition or chemical that you need to pick, right? That's really the canonical problem, right? And so for that task, right, we may not even need quantum accuracy, right? So there's another universe in which you can sort of say that that's not needed. But I think for most problems, right, accuracy at this level is actually sufficient for the discrimination task of whether this next decision is going to be better or not.
So, yeah, last question. A very basic question on the smiles of the representation of the I guess I'm curious, is there a way to deal with stereoisomers on this kind of
So chirality, so selfies, so it depends on what kind of chirality, right? And I think that's where I think you're getting to the sort of question of whether that, so a text-based representation fundamentally is dimensionality reduction, right? Chirality is inherently something that is sort of graphical in nature, right? In that if you didn't have the dimensionality, right, you can't do it. So there are ways in which you can sort of embed that, right? Yeah, or maybe it doesn't matter, and the answer you're going to get is of the racemic mixture, which is the reality of L and D, and it's going to predict some answer that's sort of the mixture of that L and D, right? So in the universe where you want L's property or D's property, that's sort of a different scenario. But I think for sort of the task of given this molecule, what's the answer, right? Maybe the racemic mixture's answer is probably okay.
Thank you very much, man.